composite Higgs models and conditions for baryogenesis. Oh, I think we're having a conversation on the microphone. So careful.
So let's start with the next lecture. It's the fourth lecture by Gustavo. And today he will address composite Higgs models and the condition for baryogenesis.
Thank you, Enrico. I have to push the button. Sorry. Okay, so quickly recast, talking a little bit about what we said yesterday. In the limit of massless QCD with two flavors, we had this Lagrangian of QCD. Okay, invariant under these transformations, SU2 transformations. I'm just going to put both of them at the same time. So this is B left. This is the U1 transformation. It's a global transformation. And then Q right is invariant under e to the I alpha right. E to the I beta right. Okay. And so the idea was that this symmetry is going to be spontaneously broken. So this is in the limit in which M up and M down are 0. Okay. And this is SU2 left times SU2 right times U1 left times U1 right. Okay. Now it's advantageous to if it turns out that the spontaneous symmetry breaking is driven by a condensate like this. Let me just do this one. It doesn't matter. Right? If this condensate is different from 0, you can see that, sure, the symmetry, these left-right symmetries are not conserved, but in particular, there is a symmetry, there is a type of combination of symmetries that is conserved, which is the vector combination. The vector symmetries are conserved. For instance, if alpha L is equal to alpha right, or if beta left is equal to beta right, then this condensate will not break that symmetry, right? Because there will be a cancellation, okay? In other words, the mass term or the mass operator does not break this part of the symmetry, whereas the axial symmetries are not respected. And the axial symmetries are when alpha left is equal to minus alpha right, and when beta left is equal to minus beta right. So this breaking proceeds as follows. Instead of writing the symmetry like this, I can write it as SU2 vector times SU2 axial times U1 vector, U1 axial. The vector currents, for example, are, instead of, if you remember, we had the currents defined as left and right, but the vector currents are, let's say like this. For the triplet current, this will be the right current plus the left current. And so it's going to be the usual vector current, but with the generator TA in the middle. And then the axial current will be defined as the right current minus the left current, and it will be your typical axial current with the gamma 5. This will be Q bar gamma mu gamma 5 Q. Okay? So now the currents are the vector currents. So similarly, you'll have, of course, the singlet current. The singlet current will be the singlet will be the vector singlet current is the one that is invariant under this transformation, right? And then, I mean, it will be conserved under that transformation. So this is the vector singlet. And then the axial, obviously, will be with the gamma 5. So we have all the currents. And now the question is, how do we represent this in the spectrum at low energies, right? So something happens. Here we have some scale, the scale at which chiral symmetry is broken, chiral symmetry breaking scale. And so what is the spectrum that I expect down here? Okay, here I have quarks and gluons, but what is the spectrum down here? Okay, now we observe the spectrum, so there is evidence in the spectrum at low energies that tells us that chiral symmetry was spontaneously broken. And what is the evidence is the existence of light particles that behave like Goldstone bosons, Nambu-Goldstone bosons. Okay, they are light and not massless because the masses of the up and the down quark are not exactly 0, but they are very small compared to the scale at which symmetry breaking happens. So how do I describe this? So the breaking now is SU2 vector cross SU2 axial cross U1 vector cross U1 axial. It should break now essentially to the vector symmetries. Okay, because this breaks the axial but not the vector. And so the number of Nambu-Goldstone bosons should be the number of broken generators, so 3 for the axial SU2 and 1 for the axial U1. Now, I'm going to tell you later that the axial U1 is not a good symmetry. It's anomalous. It sounds very bad, so we'll see. But the axial U1 is not really, it's not a good symmetry in the quantum theory. So we'll see that's what an anomaly is. So I'm not going to consider, so there's no evidence of a Nambu-Goldstone boson in the spectrum experimentally. This was a puzzle for a long time. I don't know how long, but so there was evidence of 3 pions that are really light compared to this particular scale of chiral symmetry breaking, but there was no evidence for this this eta particle being very light, and this was puzzling, and we'll understand this later, which is the anomaly in the U1 axial. Okay, so this particle has the mass of the proton, for example, so it's not really that light. But so we have the spectrum. So the U1 is anomalous, so no spectrum. So we have 3 Nambu-Goldstone bosons. We are supposed to have 3 Nambu-Goldstone bosons. And so how do we describe this theory? So what do we know about the low energy description? Well, we should have 3 massless Nambu-Goldstone bosons. The symmetries are the global symmetries are broken like this. I'm not gonna bother with the U1s in here because I'm talking about the Nabu-Goldstone bosons of the SU2A. So I'm not going to bother with the U1 vector symmetry, which is baryon number conservation, which is also anomalous, but not. I'll talk about that, of course, later because that's the main point of the whole school. So, but I'm just talking about the spectrum, and so I have to write down some field, right, that will contain the Nabu-Goldstone bosons like we always do, right? And this field should transform under the symmetry. Now, I have two symmetries here. It's a product group. So if it transforms under so let's give it these things a name. I'm going to call L, I'm going to define L as e to the I alpha LTA, right? And I'm going to call R e to the I alpha right TA. So these are just easier to write every time. So sigma of X should transform as L if this was the only symmetry, but there is also the right symmetry, so it should transform as a bifundamental not as a fundamental. So we learned that, for example, the Higgs transforms as a fundamental of SU2 left, but this one transforms at the same time under both symmetries, so it's a bifundamental. It's itself a matrix as opposed to a little column vector, okay? And so it has to fill both symmetry transformations, but that's all we know, okay? Now, what is the vacuum of this thing? Well, the vacuum choice, the expectation value in the ground state of the vacuum is going to give me a scale times the identity. Why the identity? Because the vacuum has to respect the vector symmetry, right? And the vector symmetry is not going to be affected by this vacuum choice. So this is, the vacuum is, F, 0, 0, F, okay? And so if you had, let's call it sigma 0, okay? So if you had, for example, L sigma 0, and then L dagger on this side, because this is, remember, the L equals to R is the vector symmetry. And so if I put L dagger, obviously this is fine. This is invariant. So the vacuum is invariant under this dual transformation left and right. So this is the vector transformation, right? So that's okay. It's invariant. So this choice of vacuum does not bother the vector one. But of course, okay. Now the technique to build the theory, it's very simple. If you did the transformation like this, right, what you had was, e to the I alpha TA sigma, sigma, I said sigma 0, but I'm going to generalize it, right? But let's say sigma 0, okay, times e to the I alpha A TA. So these are now, okay, so these are now the broken generators. So these are now the axial transformation. The axial transformation is left equals to minus right. This is the dagger, right dagger, and so now they don't cancel, right? So the vector transformation, they cancel in the axial transformation. So the axial would be L sigma 0 L. So this is the axial transformation. They don't cancel. Or if you want right dagger, sigma 0 right dagger is the same thing, right? is when L is equal to minus alpha L. Here is the axial. Alpha L equals to minus alpha R, then they don't cancel. So the vacuum really does a number on it, okay? And so now, you know, I have this transformation of the vacuum. And I give it a little hat to the A's, but there's still the Pauli matrix is divided by 2, but these are the broken generators, right? Okay, good. So the broken generators times the vacuum. So clearly the vacuum is not invariant under this transformation. That's fine. Okay, so now, in order to build the theory, I'm going to promote the parameter alpha to fields. And those fields will be the Nambu-Goldstone boson. So promote the alpha A to the fields. That's the recipe to build the actual Lagrangian. And then, once I have this, I'm simply going to say that the field sigma of X is going to be, well, there's going to be some F plus some, I don't want to use the letter sigma too much. There's capital sigma and little sigma, but there are historical reasons. So it's called the sigma model, and so there's all sigmas. But anyway, so I'm going to use little sigma. Here, little sigma times the identity in 2 by 2, evidently, and e to the 2i alpha A T A, you know, broken, where now alpha A goes to pi A. And since this is a field, I have to divide by the scale f to give, you know, to just cancel the units, okay? So now, this is going to be my field, and I'm going to build Lagrangians that are invariant under these transformations, okay? And so let's say, what would be a Lagrangian of this theory? Okay. I think the Lagrangian deserves more space, so I'm going to go. Okay, so I'm going to build a Lagrangian that is invariant under chiral transformations, and that's going to be the recipe to build any theory that all we know is the symmetry. Because again, all I'm using is the symmetry and the symmetry breaking pattern. So for example, in the standard model, I know that. The symmetry and the symmetry breaking pattern. And if it turns out that the scalars are composite, I don't know the details of the high energy. In QCD, we know, but we don't know the details of confinement and chiral symmetry breaking, but we do know that there are quarks and gluons. In our theories of composite Higgses, we don't, but the procedure is exactly the same. So now the Lagrangian I'm going to build, which is an effective Lagrangian, is like this. 1/4 of the trace of sigma, no, I'm sorry. I need the derivative. This is the kinetic term, d mu sigma dagger. That doesn't matter really, it's the trace. D mu sigma dagger, okay? This is a global symmetry, so I don't have to worry about covariant derivatives at this point. I could gauge it, and then but this is just the kinetic term. And then I have some sort of potential. And of course, the potential is just the usual thing, okay? Which is, so plus, so I'm going to put already the negative mass term square so that it breaks the symmetry, because I know that's what I want. So it's a plus here, divided by 4. The trace of sigma dagger sigma, this is the field, minus lambda divided by 16 times the trace of sigma dagger sigma square. This looks very familiar, right? So the potential is minus, this is minus the potential, and the 16th and the 4th are chosen so that when I take the trace of the matrices, they all cancel nicely, and then you end up with the same potential for the little sigma, for the same potential for the theory. And so the first thing we see is that the mass of pi 1 is equal to the mass of pi 2 is equal to the mass of pi 3. So these fields, which are in the exponent of sigma, clearly have 0 mass. They're Nabu-Goldstone bosons exactly. And so this represents correctly that. And then what we need to work out as an exercise is to take the trace of these things, to write the theory. Okay, so you take, you write this is minus the potential, okay, as a function of, sigma dagger sigma, and then you minimize the potential, and when you minimize the potential, the minimum should be what it should be, but it should tell you who is F in terms of M and lambda, okay? Very similar to the usual thing. Then you compute the mass of the sigma, and well, obviously the mass of the sigma would be the square root of 2 times m, because I chose all the numbers here so that when they take the trace of the matrices, everything works out. Now, so this is a theory that supposedly is, so what is the use of this theory? Well, it's telling me that many things, because it turns out that from here, I can get the pions down, right? And they will interact with the sigma and amongst themselves. So I can predict pion-pion scattering or scattering mediated by the sigma. The sigma is a massive particle. I'm going to talk about the masses. But if you want to see the spectrum here, the answer of the question, what is the spectrum? The answer is, okay, we have the 3 Nabu-Goldstone bosons at 0 mass, okay? So here we have the pions. The sigma has a mass which is of order F, okay? This is 0, okay? And then there is this scale of chiral symmetry breaking that I'll show you in a minute is essentially the cutoff of this description. So we're going to estimate how far into energies I can take this Lagrangian seriously, which is to estimate the cutoff of this theory, okay? We'll do that in a minute, okay? So, so the first thing is to realize that I forgot to smile and tuck in my belly. So the problem is the following. The width of the sigma, for example, you can estimate. Okay, let me just write the Lagrangian first in terms of sigma, so you know what I'm talking about. Okay, it's time consuming, but I think it's good. I love the smell of the smell of chalk in the morning. This is for whoever watched the movie Apocalypse Now. It's a very obscure Apocalypse Now reference, isn't it? I love the smell of napalm in the morning. Okay. It's a little dark, I know. It's a little dark. Sorry. So the Lagrangian I wanted to show you is just the same Lagrangian, but now it looks really funny because, of course, it's d mu sigma, d mu sigma, and of course I'm going to have, well, maybe I can put the mass of the sigma, sigma square. Then I have, of course, the kinetic term for the pions. So everything comes out correctly here. Okay? Then you end up minus lambda f sigma cube x. So this is a self-interaction term. I know exactly, the relationship. This is the coupling, the self-coupling, like the Higgs triple coupling had to do with the quartic and the VEV. It's exactly the same story. So we are tempted to think that you can build a model of composite Higgses with the sigmas, the Higgs, minus lambda divided by 4 sigma to the fourth. And then we have this term, which is f plus sigma squared divided by 4. This comes from the kinetic term. And then I have the trace of d mu e to the 2I pi of x ta divided by f d mu e to the minus 2I, etc. The reason why I wanted to show you this is like from here you can get, if I pick up the f in this square, so I get an f square, I get pion interactions. For example, I can get 4 pion interactions. If I pick up the sigma, then I'll get interactions of the sigma with the pi. So I get, and there are infinitely many of them. This is a non-normalizable set of interactions that I'm generating with this Lagrangian. Right? All I know is the symmetries, and when I open it up, I have infinitely many interactions that I can, of course, try to see if I can test them. Now, the one thing we know is that the sigma width, it will go like the coupling square divided by some number, I don't know, 8 pi or something, times the mass of the sigma, right? Now we observe the QCD spectrum, and we say, do we see the sigma? Some people will say, yeah. And other people will say, no. Okay? But I will say maybe. Because it turns out that the sigma is not really a bump in the pi-pi scattering. You know, if you had a bump in the pi-pi scattering, this is the sigma, this is a pion, the pion and the sigma, and then you just reconstruct the bump, then you say that's, if you see a bump, this is, in the distribution, this would be the mass of the sigma. That's not what you see. What you see is this. This is the scattering. It doesn't have, as a function of the energy of the S channel, energy square, okay? So there is no bump. So it turns out that what we know is that the width of the sigma is very, very large, or at least if you divide it by its mass, it's of order 1, right? And in fact, there are things you can do in the scattering to see if you're going through a particle in the S channel or in the T channel, but particularly in the S channel, which is to look at the phase shifts experimentally, and when the phase shift, the phase shifts of the final pions goes through pi over 2, then it has to be because it went through a pole, and that's the signal that there is a sigma. But it turns out that the width of the sigma computed this way is approximately 800 mega electron volt, and the mass of the sigma plus 800, right, mega electron volt. It's very hard to pin down the error, and the mass of the sigma is about the same. So is this a particle, or is just the strength of the interaction between pions is somehow, it takes, it's not, the important thing is that maybe what we know about the sigma is that it's quite heavy compared to the pions, quite heavy. So in principle, if you just want to talk about the pions, you can integrate it out. So that doesn't look like a Higgs, that's all I'm saying, because if you, it's a strongly coupled particle that is very broad because it's strongly coupled, because lambda is big, right? Whereas the lambda of the Standard Model is 0.1. Here, you need the lambda to be quite big to get these kind of things, okay? So that's the first lesson. The second thing that we need to understand is what is the validity, the cutoff of this theory? The validity of that Lagrangian for understanding the interactions, at least of the Nambu-Goldstone bosons, Okay, so the sigma lives at the sort of the edge of the validity, but what is exactly the validity of the theory? And there is a procedure that's rather simple, which is you take an amplitude that you know how to compute in the theory, you compute, well, let me just describe it. So cutoff of the theory, okay, how do I estimate it? First, I'm going to compute the amplitude, you know, pion amplitude, scattering. This is generic. Of course, if these are plus or minus, this could be plus or minus, so 0, 0, there are factors. But this is, I'm going to do the generic argument. It comes from this term, okay? And typically, there is no way to avoid the fact that it's going to be 2 powers of the momentum in the amplitude. There's going to be, because that's how you get 2 pions. Each time you get a pion, you get a factor of 1 over f, whether there is a momentum or there is no momentum, right? Then I'm just using this part here to get only pions in the interaction. So I'm not using the sigma particle. And so I get an f squared, right? So this will go like, you know, the f squared times p squared over f to the 4th. So the amplitude of pion scattering scales as the momentum squared, the momentum, let's say the center of mass momentum of this reaction over f squared. Okay? So this is the 3-level scattering. So now I'm going to try to use this vertex to compute a loop correction. Right? So that's the loop correction. So how is it that I'm going to compute the loop correction? Well, I have to do an integral. So, you know, d4, there is some momentum k that I have to integrate over. There is a d4k divided by 2 pi to the 4th or whatever. Then I have these 2 vertices, but you have to be very careful because in each vertex, I'm going to get a momentum from the external momentum, but also a momentum from k. So this is going to work out. So there are 2 propagators, right? But the vertices depend on p squared, on p and k, and on p and k, right? And so now it's going to go like this. It's going to go, this is a back of the envelope, or I don't know, quick calculation, p squared, k squared over f to the 4th. And then the propagators, there are 2 propagators. I'm going to put 1 over k to the 4th just to estimate the ultraviolet behavior. I'm not, you know, that's why I don't have masses. Well, they're massless anyway. I don't have eyes or anything. And so when you do this calculation, you know, you rotate to the Euclidean blah, blah, blah. You have a cutoff. This goes like k cubed dk times some angle. Then you have, you know, a k that when you integrate is k squared. So it's quadratically divergent, right? And so it goes like p squared divided by, okay, it goes like, okay, p squared divided by f to the 4th, sorry, f to the 4th, times the cutoff square divided by the loop factor, 16 pi squared. Now I can write this as p squared divided by f squared. Now p squared divided by f squared is the 3-level result, right? Times the cutoff square divided by 16 pi squared f squared, okay? So now, this is the result of the loop calculation, and this is the result of the 3-level. When does the theory break down? When both of them are approximately the same. So I cannot trust this calculation of the loop because I went too high in energy, right? And so when lambda, when this is equal to 1, that's the cutoff. Because now the loop is exactly the tree level, okay? And so that means that the cutoff is 4 pi f. So I can trust this theory to 4 pi f. And how do I know f? Anybody knows how do I know f? This is proportional to f. It turns out that I know that the pions, since they are Nabu-Goldstone bosons from back when I said that the Nabu-Goldstone bosons have to have the same energy as the vacuum, that there is a charge that doesn't annihilate the vacuum, but takes it to some other state, alpha, I called it, but there's a charge that takes you to the Nabu-Goldstone bosons. So this matrix element is not 0 when you have Nabu-Goldstone bosons, right? And the thing that's in the middle is the broken charge, is the axial charge, right? Here you have to have an A here, right? Mu, and here is pi, let's say B, but actually there is delta AB. And so this is going to be proportional to the momentum and delta AB, okay? And so F can be measured in pion decays. Pion decays to particles that are not hadrons. For example, pi going to mu neutrino of the muon implies F is approximately 100 MeV, okay? And so basically the cutoff of the theory, it's about a GeV, okay? That's the cutoff of the theory. Of course, it's a very naive calculation, but when you're an arrogant theorist, you even give it a fancy name to the naive calculation, and it's a very famous paper called Naive Dimensional Analysis, but this is what it is. It has more citations than most papers, and it's just this, okay? All right, good. Now, so we want to have a theory of electroweak symmetry that is like this. It's like QCD. In QCD, the scale of chiral symmetry breaking is given dynamically by some theory, which is color. But now, what I want to do is to have a theory called technicolor or something else that will give me the same result at low energies. So now we are at low energies, at the LHC are low energies, okay? That's how we see it as theorists. So we live at low energies, and the weak scale is at low energies. And I want to have a theory where the Higgs, it's in this spectrum of low energy, right? So this is the Higgs. And it turns out that the problem with this, let's say that I do the same thing. I just repeat this theory. I'm not going to do it again because it's the same theory, right? But I need a coupling. I need a coupling like the QCD coupling, getting strong in the infrared, more or less here. And this should be the electroweak scale. This should be the electroweak scale. So this is lambda, not QCD, but techni-QCD, right? And should be hundreds of GeVs, not MeVs, right? F in this theory should be 250 GeV, the vacuum expectation value of the Higgs, which here is the vacuum expectation value of the sigma. Now, I ask you, from what you know about QCD and what you know about the spectrum of the standard model, is this going to work? Come on. A little interaction. Is this going to work if I call the sigma the Higgs? It's not going to work because what happens is that, okay, let's say that I built a technicolor. You know, these are technique works. I don't know. Technique works will create F electroweak and then I have sigma. What happens is that the mass of the sigma, okay, the mass of the sigma should be quite big, okay, and it should be, in fact, out of the spectrum. And strongly coupled. So this identification of this particular scalar with the Higgs, which was the first obvious thing to try, I mean, this is an honorable thing to have done. So for you to know, this was done by some guy called Weinberg, Steven Weinberg and Susskind in 1977, okay, about 10 years after the standard model, a model of leptons was published, right? Very, very good people, fantastic people, the best people, okay? It's okay? Can I go now? I worked on it too. So now we know too much. We know that the coupling is not of order 1, it's 0.13, that the Higgs is 125 GeV, is narrow, is weakly coupled. Everything's wrong with this, okay? So what do we do to try to use the same picture? Because otherwise I wasted your time. Well, what we do is like, well, wait, if you look at the spectrum of this theory, we still have something that we can use that is light, and they are the Nambu-Goldstone bosons, right? So I need to cook a theory where the Higgs is a Nambu-Goldstone boson. And that's really the composite Higgs models that are used today. Okay? The modern version of composite Higgs models is a version in which the Higgs is a pseudo-Goldstone boson, Nambu-Goldstone boson. I always put Nambu in there, but especially if Rogerio is around, I have to put Nambu in there. Because, you know, I'm a Chicago guy. Chicago boys. Okay. So here, here is the gist of it, okay? That's not what I meant. Yeah, okay, it's this. It's an Nambu-Goldstone boson. So in principle, here is the mass of the Higgs, okay? And here is the cutoff of the theory, 4 pi v approximately, okay? That's really, you know, what we've been learning. So 4 pi v is the cut. I'm going to describe the standard model as particularly the Higgs sector, as if the Higgs was a Nambu-Goldstone boson of a spontaneously broken global symmetry. It has to be global, okay? But since it's not really massless, we know it has 125 GeV of mass, then we need to break explicitly the symmetry, the global symmetry, in the same way the quark masses break explicitly the chiral symmetry and give the pions a mass. So it's the same story. The pions have 140 MeV, the Higgs has 125 GeV, so there's got to be some explicit breaking, and it turns out that the easiest way to do this is to have a global symmetry that includes the standard model inside. And so since the standard model is gauged, the gauge interactions break explicitly the global symmetry, okay? So here is the way to do it. So I need how many Nambu-Goldstone bosons minimum? I mean, just to make out the Higgs. How many Nambu-Goldstone bosons I need? How many particles how many real scalar fields I need to put together a Higgs doublet? 4, okay? So I need 4, at least, you know, Nambu-Goldstone bosons. The minimum is 4. I need, so a global symmetry group breaks spontaneously, and it gives me this spectrum of Nambu-Goldstone bosons. But this is including the standard model gauge group, particularly the electroweak standard model gauge group. So the gauge group is, so here is the picture. Here is G. There's a subgroup of G, which is H, which is the unbroken generators of the global symmetry. Now, inside H, I'm going to have, inside H, I'm also going to have the standard model, which is gauged. Now, the gauge interactions and also the Yukawa interactions of the standard model do not respect this large global symmetry. And so they break it explicitly, and they will generate a potential or a mass for the Higgs. That's the idea, okay? That's what the composite Higgs is. And most of what we've done builds up to how people actually do this, okay? And so the only thing that you need is to pick the global symmetry to start with, to get the minimum number of Goldstone bosons, right? So in principle, you would imagine, for example, so what's G? Choice of G, right? Let's say that you break SU3 down to SU2 cross U1, just global, right? Global. Then, of course, you're going to gauge this, which is inside here, so everything works, right? If this was G and this was H, and H coincides with the standard model, right? Then let's count number of Goldstone bosons. I have 8 generators here, unbroken 4 generators, so 4 broken ones. So that checks out. I have 4 broken generators, 4 number Goldstone bosons. The problem with this choice is that it's excluded by experiment. And it's a long story, but there is a problem with this choice that it does not possess, it doesn't have a SU2 custodial. This is not color, it's custodial. It's a global symmetry. And this global symmetry is an accidental symmetry in the standard model spectrum, which tells you essentially that the mass of the W square divided by the mass of the Z square times the cosine theta square, the Weinberg angle cosine theta square, is 1 plus very little corrections from loops. And so in this pattern of breaking, this will not be 1 at tree level, okay? So it's an experimental fact that this choice, although it's very minimal, doesn't work, okay? The next choice that does work it's a bit off-putting at first, but it's relatively easy to work with. I'm not going to go through the details. But the composite model that does work it's called the minimal composite Higgs model. And it's not just minimal because it has just 4 Nabu-Goldstone bosons. It's minimal because it's the minimal with this custodial symmetry in it built in. And so G is SO5. And it's broken down to SO4. So that's the spontaneous breaking, okay, of this global symmetry. How many generators here? 10 is 5 times 4 divided by 2. This is the rotation group, so it's the number of angles, right? Angles in this 5-dimensional rotation group, right? It's the rotation group without the reflection. That's the S, right? So there are 10 generators here, and there are 6 generators here. So correct the coset space. So the dimension of the coset space is 4 Nabu-Goldstone bosons or 4 broken generators, okay? It's 10 minus 6, okay? Good. So So those 4 broken generators then, now I told you about this custodial symmetry. Who is going to be gauged now? And who is going to be, so what do we gauge? So first of all, let's notice that H, which is SO4, can be written as, or is isomorphic, whatever your inclination is, as the product of 2 SU2s. Okay? So if I gauge one of them, like this, I can use the other one as it's just a remnant of the global symmetry, H, which is not broken spontaneously, and that's the custodial symmetry. So this is the minimum size of a global symmetry that will have all of these ingredients, okay? There are other problems with hypercharge that I don't want to go into. What I want to go into in the 7 minutes that I have before I change completely subjects is, so when you gauge this, okay, and also when you include the Yukawa couplings are not going to be giving you this. So let's just write the Lagrangian. Okay, the Lagrangian, of this thing without the gauge. But okay, let's put the gauge in. Let's say the d mu sigma dagger d mu sigma is our friend, minus some coupling that I'm going to call G star squared divided by 8. This is choices. And now we have sigma as actually, well, no, now I have to do the dagger. Here, I don't need the dagger. It's just transpose, I'm sorry. The reason is that this is a real group. So it's just the transpose. And so who is, but you can put the dagger, it doesn't hurt. It's just the same story as before. And this, I'm sorry, this has to break the symmetry, so I'm going to do this. Sigma dagger sigma minus f square square. So I can already, I'm telling you that if you minimize this potential, you're going to get f as the minimum. Yes?
I got a little confused about the SU2 custodial because you have to gauge it to have the U1, right?
Yes, I'm going to gauge this is going to gauge, and but this is the gauging that breaks the custodial symmetry in the standard model.
Ah, okay, okay.
Which is G prime.
Okay, yes, yes.
So this is the gauging. This is the gauging that breaks the custodial symmetry as the standard model breaks the custodial symmetry. Mm-hmm. Right? The custodial symmetry is an exact symmetry in the limit of G prime equal to 0, right?
Yes.
But when you put in G prime, you still have this 1 here.
Yeah.
Right? Because it's the cosine,
yeah.
appears here.
Okay.
In the limit, so in the limit of G prime goes to 0, the Z mass is the same as the W mass because it's W3. Mm-hmm. The Z is only, it's A3, okay?
Okay, great,
so,
thank you.
All right, good. So, good question. Anyway, so it's funny because I thought I already wrote the Lagrangian. Okay. So now I'm just going to tell you what sigma is because there is no mystery what sigma is. Once you have sigma and the Lagrangian, you can see what happens in this theory. You built the theory, and so. What are you going to say about the vacuum? First, the choice of the vacuum, which I call, again, sigma 0, is going to be, in the fundamental representation of SO5, I'm going to have to count zeros, 1, 2, 3, 4, F. Okay? Not much of a complication. It's, it's a big group, but, that's the vacuum that I'm going to choose. Clearly, it preserves SO4, which, leaves is going to annihilate all the. If you put all the generators of SO4 embedded in SO5 in the upper left corner, which is only so you put the generators of SO4, and here you have zeros, and here you put SO4. clearly SO4 generators are going to annihilate this vacuum, so that's why it's preserved. Okay, that's the choice. Very good. Now, the field sigma, then, the field sigma, following what we did at the beginning, is going to be, well, I know who the Nabu-Goldstone bosons are. They are the component of the Higgs. So I'm going to write them as this. E to the I, H, A, T, A, divided by F, times, 0, 0, 0, 0. And now here I have F plus our villain sigma. Okay, I have to have sigma because it's a radial excitation that will always be here, right? But sigma, I know it's going to be heavy, and I'm going to integrate it out. And at low end, so it's going to be a resonance, right? Like in QCD, you have resonances. But the Nabu-Goldstone bosons are much lighter compared to the resonances, right? Now, the mass of the resonances are typically given by G star times F, okay? G star is this coupling. When you get the masses from here, the sigma resonances will come from here. It's the only one that appears in the potential. So G star F. F is the weak scale. So if the resonances are to be heavy compared to the weak scale, then that means that G star has to be, bigger than 1, has to be a strongly coupled sector. So the resonances are strongly coupled. For example, the rho resonance, which is a resonance in QCD, you should all know the rho and the mass of the rho, okay? Even if you're doing string theory, my opinion. So hopefully you don't get me as a qualifier exam professor asking questions. But the rho is about 800 MeV. The pion is much lighter. But the rho couples to the pion. How does it couple? With the coupling that is about 6. The rho coupling is a number 6. G rho power pi is 6. So it's a large coupling, and the resonance becomes broad, although the rho is not as broad as the sigma. And that's a strongly coupled sector with large masses, okay? But the pions are the Higgs, okay? And so I'm going to write for you the sigma field in a way that this is probably an exercise, F plus sigma of X. And then here, if you put in the generators of SO5, this is an exercise. The generators of SO5 are relatively simple to, the broken generators. The broken generators, these are the broken generators. I don't know, IJ are I don't know, this is square root of 2, and then there are delta. There is a delta, so there is a J5 and an A, and there is no, I think it's the I first, okay, and the J5, right? Minus the J5 with the I5. So these are just, if you look at the generators of rotation, right? The generators of rotation have this structure. There are 1s in some place. If you're rotating about some axis, there is a 1, and 0s everywhere else. That's just the same thing. So these are relatively simple and if you use them, then you end up with a very funny structure here. There is a vector H, which is essentially H1, H2, H3, H4. So it has the depth of 4, divided by the absolute value of H, which I'll define by the H absolute value, which I define in a minute, times the sine of H over F. The sine, because if you're going to have a cosine plus I, the sine, the composition, once you put in these ones, with H1 and H2 and H3 and H4. So H here is this. H3 plus I H4 and H1 plus I H2. And so what I called H is this vector, right? H1, H4. And then, then H is the, absolute value of this product, right? And so if you write it like this, and then there's a cosine of F of H over F, where H is the Higgs field all combined, right? Then you can actually compute all the interactions, for example, with the gauge bosons of the Navier-Walton bosons, which are the Higgs. And everything comes out almost like in the standard model, but there are going to be modifications. And so, first of all, we're going to choose that the Higgs is, eventually the Higgs is going to have a vacuum expectation value. That's a different vacuum. This is the breaking of the gauge symmetry, right? So eventually, at some, so the scale, let me start here. The scale F is somewhere, okay, which is the masses of the sigma and the resonances, right? And the scale V, in principle, in this theory at the moment, I haven't told you what it is, but it's lower. And so when V is acquired, when this is equal to V, or V divided by the square root of 2, right, you choose one direction, which is typically H3, acquires a vacuum expectation value. And so the rest of what you're going to do is pretty clear. But these angles, when you put in the vacuum expectation value of H, which is this, right? The vacuum expectation value of H will go like V, right, over F. And so there's going to be a parameter in this theory that is going to appear in all the couplings, which is the cosine of V over F, right? And that is going to suppress all the couplings of the standard model particles to this composite Higgs. So there you have a first consequence of this. So first consequence is all couplings of the Higgs are suppressed and they're going to be suppressed by this factor, which I cannot derive, but essentially there's going to be some F squared times the sine square of H. This is the field divided by F, right? And this, when you expand this, you get V squared and 2V squared and the square root of 1 minus, if you expand for the VEV around the VEV of the Higgs, V squared over F squared times H of X, plus there is another one that is of interest, 1 plus 2 psi H squared of X, plus you keep going. Again, this is a non-normalizable theory, just like the sigma model was, the nonlinear sigma model was. And so in this case, what happens is that every time you have one Higgs coupling with somebody, its coupling will be suppressed by this number. In particular, for example, G H vector boson goes like 1 minus psi squared times the standard model coupling. And this is true VH. And then HV goes like 1 plus 2 psi the standard model coupling. Similarly, the Higgs coupled to the fermions will be suppressed by this very same. I define this parameter. I'm sorry, one monoxide. Psi is defined to be v squared over f squared, right? So if you want, we already know from the measurements at the LHC that f has to be somewhat bigger than v. So LHC measurements imply that f over v has to be about bigger than 3. So 750 GeV, more or less, is the lowest scale f. Okay? And so that's that. Now, what about the hierarchy problem? Well, I didn't say anything about the hierarchy problem, right? But again, this theory has a cutoff. So there's no, I cannot take this theory, right, of a composite Higgs as an Nambu-Goldstone boson and use it up to the Planck scale. The cutoff is 4 pi f. So there is no hierarchy problem as long as f is not really, really high. So the hierarchy problem is not really solved. It's just deferred because above 4 pi f, I'm supposed to have some new theory of the components inside the Higgs that comes in, okay? So the theory here, 4 pi f, and so 4 pi f it's about 7 TeV, let's call it 10 TeV, right? Because of these limits, right, from the LHC. Here are the resonances, I don't know, the rho or whatever, which are around f times g star. So the LHC could actually try to find these resonances. There are vector resonances, there are fermion resonances, there are all kinds of resonances. And here, of course, is the weak scale with the Higgs as an Nambu-Goldstone boson. But then what happens here, I don't know. So this is a very, as I advertised earlier, unlike the case of Susie, it's a very modest solution to this hierarchy problem, is trying to understand where the scale comes from, just like in QCD, but I don't know what happens afterwards, unlike the case of QCD. The QCD, we know there are quarks and gluons and SU3 color. Here, I don't know. People have tried to UV complete, but the UV completion is unknown. And it comes above a very modest cutoff of about 10 TeV, okay? Okay, so this is the philosophy of composite Higgs models. I don't have time for details, but I'm going to stop right here. Maybe in the discussion we can ask more. Wait. I still have things to do. I still have time, right?
Oh, yes, but if you want to...
Are there any questions about this before moving to the last thing?
About this model, the first one, it's the little Higgs model, right?
I'm sorry?
This one is little Higgs model, right? S3 going to S2 cross U1, or not?
No. In order to be a little Higgs, I need collective breaking, so I need two SU3s.
Ah, okay. But my question is...
This is very minimal. A little Higgs is not that minimal, yeah.
Couldn't you kind of impose some symmetry in order to avoid this kind of grid corrections on the rho parameter? Because sometimes we don't have the custodial symmetry in composite Higgs model, but impose kind of a C2 symmetry, Z2 symmetry to not have this.
Sure. The easiest thing is to try to reproduce the accidental symmetries of the standard model. Mm-hmm. But if you want to reproduce the experimental values instead of the symmetries, you can do that. It's very dangerous.
Yeah, I know that.
Because you always get three-level corrections that you have to suppress by some, specific mechanism, like a Z2 symmetry or something.
Okay, another quick question. If I would like to make kind of a step breaking, in the meaning I could start kind of a SO6 and make a break up to SO5, after that SO4. How can I do that with the model?
You can do, okay, there is, I probably should show with you this table. There are at least 20 things you can do, but in most cases, you get more Nabu-Goldstone bosons than 4. And so you get other Nabu-Goldstone bosons, and some people use SO6, and then you get something that somehow with the Z2 you can make dark matter, or you can make a light singlet Nabu-Goldstone boson that acquires some mass somehow, and maybe will give you a first-order phase transition together with the Higgs. You can do all kinds of things. I just did the minimum, but the philosophy will be exactly the same, right? Will be exactly the same. You need to respect some global symmetry, spontaneously break it, gauge the standard model as a minimum to break explicitly, and blah, blah, blah. So this, I was just trying to give you the procedure, but you can build a model with any global symmetry spontaneously broken, and people have done this and all the way to, I don't know, SO8, SO10, I think people have done. So I don't have time to go through those, but okay. It's very, very similar, right?
Okay.
You just find the generators, the vacuum that respects the symmetry that you want. It's exactly what we did in QCD and here.
Okay, good. Thank you.
It's the philosophy is that.
Other questions before we switch topic?
Yes. Professor, sorry, I don't know if you comment about this, but what happens when we are above this scale? Like, what the other particles we embed then in this SO5 representation? Like, what happens to the other particles?
Which other particles?
I don't know, because you broke SO5, then you to SO4, and then this would like the standard model. It's inside this symmetry group. So when you are, if we go above the scale, we need to describe the particles that we have in these quintuplets or something like that.
Okay, so here is what we know is the standard model, right? Now at some scale, F times the coupling, I'm going to see the resonances of the theory. And the resonances will be resonances that come in multiplets of SO5, right? Mm-hmm. And these multiplets, some of those resonances, since, for example, the W and the Z generators are inside SO5, will be copies of the W and the Z, but heavier. But many others will not, will be generators that were broken. And so there'll be resonances up here. There will be an enormous number of resonances at some scale. So those particles that are vector resonance, and also, so suppose you have a fermion, you need to embed the standard model fermion in an SO5 representation, and it turns out that only the standard model ones will be light, but then all of the other ones will not be light, right? You can arrange for that, but they will have resonances here. So all the other, let's say that I have the top and the bottom here in the left-handed, there'll be these psi1, psi2, psi3 objects here. They only have resonances. They live up here, right? Mm-hmm. That's because the pattern of breaking from SO5 to SO4 gives me the SU2, and so I am allowed to have this. Remember that these guys get masses through the breaking of the Higgs, right? Whereas these guys get masses through the breaking, or all of them. You know, the resonances gets masses through F, so they live at a higher scale, right?
I see. Thank you.
And of course, there'll be resonances of all of them, including the top, right? And the bottom. Yes.
My question is, I didn't understood completely what sigma is. Like, is there one of the H's will be the physical Higgs, the other 3 the eating up Nabu-Goldstone bosons?
Yes. So this is the Higgs. So this will go into H plus V over the square root of 2, like usually. And this, and this will be eaten by the W and the Z, like usually. This is the Higgs doublet of the standard model.
Okay,
Yeah.
and the sigma, what is the sigma that
The sigma is a resonance that we observe only when we go to this scale of energies, which supposedly, okay, we already, we have LHC bounds on the masses of the resonances, and so I know that F over V has to be bigger than 3, and that means that, these resonances have to be heavier than something, but they should be there somewhere to be found at the LHC.
Okay, but it would be the same sigma of QCD?
No,
But
it's
another sigma.
it's a heavier sigma.
Okay.
It has like several TeVs, hopefully, a TeV mass, whereas the sigma of QCD has 800 MeV mass, which is, and that's a particle that exists or not, but that's because people, discuss what a particle is. But it's there. There is something going on in QCD. This is completely speculative, right?
Okay.
The sigma, I'm sorry I call it sigma, but it's just so suggestive that,
But we are like predicting another resonance with this
Oh, many,
theory.
because, for example, what I call the row here is actually, there is a W resonance and a Z resonance, right? As well as resonances that don't have standard model counterparts that are light, because they are representations of the broken generators of SO5, but they can have resonances given by G star times F. So there's a bunch of resonances. Some of them look like standard model particles that are heavier, and others are completely new.
Oh, okay, thank you.
Okay, I suggest that we leave other questions for the discussion.
Okay.
We switch
So very quickly now,
to the
very
baryogenesis
quickly, I have to tell you a quick story. Okay? A quick story. And then the story is, we're going to go back to the standard model now. And here is the story. The story is that it starts with anomalies. What's an anomaly? An anomaly and I'm going to tell it, because otherwise I take too much time. An anomaly happens when a symmetry of the classical theory, the classical action, for example, is not respected by quantum corrections, okay? And that's called an anomaly. For instance, if I write QCD, like I wrote it before, without masses of the quarks, that theory, in principle, classically is scale invariant. However, when I do the quantum corrections, the coupling in the covariant derivative depends on the scale mu, and that's a breaking of scale invariance, it's explicit breaking, and it's called the scale anomaly. The scale anomaly, that's an anomaly. But the one anomaly that I'm worried about is anomalies of symmetries that, and I'm just going to give an example. In particular, if I have theories, so chiral anomalies, if I have theories that have chiral couplings, gauge theories or global theories, in other words, there's a gamma 5 somewhere that selects left, it tells you apart left and right, then it turns out that you can show that triangle diagrams where you have some gamma 5, gamma mu, gamma 5, and here you only have gamma nu and gamma alpha. These theories, these are vector, and this is gamma 5. And then it turns out that this theory has an anomaly when you compute these quantum corrections. And then the anomaly is the fact that the axial current, let's assume that this is QCD, and these are gluons, right? So there are some TAs and TBs here, but this is actually the axial current, okay? Now, if the axial current, if I take the doublet of the axial current, if you remember, there was one with the sigma A divided by 2, that's not anomalous, but the U1 axial, if you compute the U1, then it turns out that you get an anomaly, which is like this. That I have to write once. I call it G, right? Okay. So it turns out that now, even in the absence of the masses of the quarks, remember that the axial the axial current is only conserved in the limit of massless quarks. Even in the absence of them, there is this anomaly. And this is really a quantum effect, okay? It's nice to know where the anomaly comes from. Because I'm sorry? I'm sorry, what? I can. Oh, of course. Yes. Thank you. I was going to do the dual, and then I stopped in the middle, and I did the average. Okay. Thank you. So there is a way to write this in terms. Well, never mind. I'll do it later. So there is a very interesting way to understand the anomalies and why they where they come from in the functional integral, which is very useful. In the functional integral, if you're going to do a chiral transformation in the functional integral, and let's say that you have something in here, some theory, but now you do a chiral transformation where psi goes to e to the I, some alpha times gamma 5 times psi. So this is an axial, this is a chiral transformation. It turns out that when you do this transformation, although the action, which is the classical action up here in the functional integral, is invariant, the measure is not. There is a Jacobian, and this Jacobian is not 1. Okay? And that's the anomaly. Okay? So the Jacobian, if you compute the Jacobian, is exactly what it will give this anomaly up here. So this shows you that this is a quantum effect because it comes from doing a chiral transformation on the functional integral, on the measure of the functional integral, which is how you quantize the theory. Okay. Now, moving on real fast, this is why, for example, why the U1 axial is not a symmetry, because it has an anomaly even in the absence of mass for the quarks, okay? And so that means that the mass of the eta Goldstone boson from the spontaneous breaking of the U1 axial is approximately 1 GeV, which is the cutoff of the whole chiral symmetry breaking story. So it lives at the cutoff, not next to the pion, okay? Good, it's an anomalous symmetry, okay? Now, is this really, I mean, what would have happened if I put electromagnetic fields here? These are vector, just QED. What would have happened? Well, I would have obtained something like this without these indices and with the electromagnetic field. Does that mean that somehow electromagnetism drives an anomaly of some kind? And the answer is no. And this is important for what comes later, for baryogenesis, or at least electroweak baryogenesis. The answer is no, because it's not enough to have this anomaly, and this quadridivergence of the it's not enough to have this quadridivergence of the axial current, for example, being non-zero. But the Jacobian really is an integral. So when you look at this, you need to know if I'm going to write it like as g squared divided by 32 pi squared d for x f. Whatever now the non-abelian field is f, could be SU2, could be f a, I'm sorry, dual mu, where the dual, I'm going to define it here, f dual mu nu is 1/2 epsilon mu nu alpha beta f alpha beta, okay? Okay. Now the problem is, so this integral has to be different from 0, okay? Because the Jacobian is really the integral. It goes in the theory, the Jacobian becomes e to the I, the integral of this anomaly, d for x. And then I can put it in the in the theory. You know, I can add it to the theory, to the action, and then this will drive this this equality here. Okay, and so this is what has to be different than 0. Okay, the reason why this is a problem is because I can write the anomaly like this. I can write, for example, f dual. As a quadridivergence, d mu of a vector, right? And so, and I can write this vector. It's a complicated vector. So k mu is epsilon mu nu lambda sigma times a sigma f lambda sigma plus 1/3 FABC. There is an A, and here there is another A, FABC, and then there is A, B, and AC, nu, lambda, and sigma. So this is a complicated way of writing it, but since it's a 4 divergence, then you ask yourself, well, the integral of 4 divergence should not matter. If I go to infinity, there are no sources, then this is what we always say. Somebody said that the other day, if you go to infinity. Well, it turns out that, as was mentioned at some point yesterday by Misha, there are some gauge field configurations where this is not the case. There are some gauge field configurations that will not allow you to throw away, so where this integral is not a 0 contribution to the theory, and those are driven by instanton effects. Now, when this is the case, is that there are large gauge transformations, as were mentioned by Misha, that drive field configurations. Is these field configurations simply do not allow you, I mean, you will get a non-zero answer for this. And I don't have time to give examples, but I can actually, you know, show you an instanton solution where this is not 0. You can compute this integral. And one of the things that you can show is that this integral, it's going to be proportional to a topological charge, right? And that's the next step. The you know, essentially, when you do the integral, you get a topological charge, which could be 0, in which case the whole thing is trivial, but it could be non-zero. And this has to do with the topological structure of the gauge group that drives this object here. Now, somebody asked, why is it this doesn't happen for U1? It doesn't happen for U1 because you don't have non-contractible mappings in U1. All the mappings are trivially contractible to a point, and so all of the topological charges are the same and equal to 0. But if you have an SU2, there's always a solution that you can find in SU2, or an SU2 subgroup of your non-abelian gauge theory. For example, SU3 in QCD has this SU2 subgroup. And these instanton solutions will drive a non-zero answer and will tell you that then there's an anomaly, right? if you can actually find a solution. So there has to be an SU2 subgroup. So this is true in SU3 QCD. It's also true in the electroweak theory. The electroweak theory has these solutions, and typically what happens is that this topological charge is okay. It's a nice experiment. What's the minimum size to break that chalk into 3 pieces? And so to conclude, is that okay? To conclude in the last minute, I'm going to make that connection. So the topological charge, if I have this D for X, F mu nu A F dual times this G squared divided by 32 pi square, okay? This is going to be equal to a number n. There is a theorem behind this, and I don't have time to show this theorem, but it's a mathematical theorem, and it has to do with something called the Cartan-Mauer form that is behind the fact that each of these gauge fields, this part will not contribute, but each of these gauge fields will actually, if you start from the vacuum, right? And you say, well, I have the vacuum, and the vacuum is nothing, including all the gauge fields are 0. But of course, the gauge fields can be gauge transformed, and this gauge transformation is just the derivative of some coupling, right? The derivative. So you have, 1 over the coupling d mu of G times G to the minus 1, where G is a gauge transformation. This is the A mu field from the vacuum to a gauge transformation. And if you have 3 of these, like here, integrated over with an epsilon tensor, that's a proportional to a topological charge. That's a theorem, mathematical theorem, Cartan and Mauer forms. And so it turns out that you can write d mu, k mu, or the anomaly in terms of this index topological charge, which is an integer. And this, not have time to tell you this, this is what's behind the vacuum of QCD being, in principle, indexed. So this is the vacuum with topological charge 0. This is 1. This is minus 1, 2, whatever. Okay. And of course, in order, so in the case of SU2, you can do the same thing, and you'll have this vacua, and you can, in principle, tunnel, right, and compute the tunneling rate. And the tunneling rate is extremely suppressed. Is typically 1 over G squared. Maybe there is an 8 pi here, okay? And so the tunneling rate is extremely small. And so this is not particularly important. We don't have to worry about this. The standard model Lagrangian has this accidental symmetry, which is baryon number conservation. But this is not a problem for happening suddenly. However, so baryon number, which is e to the I some coupling alpha baryon times some. So this is that's a quark, and a U1. This is a U1 baryon number transformation. You can also have lepton number, e to the I some lepton transformation, and this is the lepton here. This is U1. This is the total lepton number here. These are accidental symmetries in the standard model, but you can show that both of them are anomalous. And they are anomalous because the current, a baryon current, here, let's say that you have a baryon or a lepton current coming in here, it could have a triangle diagram with the standard model gauge bosons, like the U1 hypercharge or SU2, that are chiral, so there will be gamma 5s here. This is a vector current, but there are gamma 5s in one of these two, then this will give you an anomaly. both for the leptons and for the baryons. Luckily, the anomalies are the same. So d mu j baryon mu is equal to the number of flavors divided by 32 pi square, the coupling of SU2 square, and then here is the SU2 FF dual. Why the SU2 only? Because the U1 does not have an anomaly, which we covered that. And it's exactly the same for the lepton. The lepton number has the same anomaly. This is the number, I'm sorry, of families, not flavors, right? Generations, right? The number of generations. And so in the standard model, these currents, so let me put it this way, the integral of these currents, B minus L is conserved because there are anomalous, but they have exactly the same anomaly, so the difference cancels, whereas B plus L is violated. Because here you can have, for example, the gamma 5, some gauge interaction, and here is just a vector interaction, and that's the violation. So anomalies are important in trying to understand baryon number violation in the standard model, and of course, everything you've heard about thermal field theory will allow you to think that tunneling at 0 temperature obviously is extremely suppressed, but maybe at high temperatures, you could go over the barrier and violate B plus L, right, in the SU2 theory. There is an extreme here, which is not the vacuum, evidently, and this extreme is a classical solution of the equations of motion. It's called the spharodon, and is the minimum energy you need in order to be able to violate this number, this index, which in the case of this anomaly is baryon number. So I'm sorry I had to go real fast on this, but I had to cover it. That was what was asked, and I'm going to stop here. Sorry for the delay of lunch.
One or two quick questions. There is one in the chat. How the composite Higgs model deal with little hierarchy problem?
Okay. So the little hierarchy problem is the only thing that actually the composite Higgs models solve, in a sense that what's the little hierarchy problem is the fact that new physics does not seem to be around all the way up to, say, 5 TeV, according to the experiments. And so 5 TeV is already much farther away than from 125 GeV than you would have expected from the hierarchy problem. So that's the little hierarchy problem. The big hierarchy problem is going to, I don't know, the GATT scale or something, right? And so the way you deal is to say, well, there is a cutoff, there is a theory below a cutoff, which is 10 TeV, which is about the little hierarchy problem, and then you solve the physics in between. You protect the Higgs mass between the mass of the Higgs, between the weak scale, and that cutoff, which is 4 pi times the new scale of the global symmetry breaking, which is F. So it's in that sense, that's how modest composite Higgs models are. We solve the little hierarchy problem, and so that's the only one that we solve. And then after that, there is new physics that we are not even assuming, but it should be behind the breaking of this global symmetry and the degrees of freedom, new quarks and new gluons or whatever, that define this new scale F. That we're not even addressing. I mean, some people are, but it's not in here.
Okay, so I suggest we stop here. It's time for lunch. And we reconvene at 2 p.m. So thank you for the nice lecture to Gustavo.
Okay.